In the composition video of the electrolyte, we briefly mentioned the characteristics of an ideal solvent and introduced some commonly used solvents. In this video, we will provide a more detailed explanation of the electrolyte solvent. The electrolyte solvent is an important component for ion conduction between the cathode and anode inside the battery. In this process, the solvent plays a significant role. An ideal electrolyte solvent should meet the following requirements. The first requirement is to have the ability to dissolve salts. The solvent needs to dissolve the electrolyte salts to a sufficient concentration, so it requires a high relative dielectric constant and polarity to ensure that the salts can be fully dissolved. The second requirement is to have low viscosity. The solvent should have low viscosity to facilitate the conduction of ions to make the ion migrate rapidly within the battery. The third requirement is chemical inertness with battery materials. The solvent must remain chemically inert to all components in the battery, especially during battery operation, and should not react with surfaces of cathode and anode. In lithium battery, the cathode and anode have strong oxidizing and reducing properties. The reduction of protons and the corresponding oxidation of ions typically occur at 2 to 4 volts versus lithium, which falls within the charging potential of lithium battery electrodes. The potential of anode is 0 to 0.2 volt. For cathode is 3 to 4.5 volt. Therefore, protonic solvents cannot be used. The fourth requirement is maintaining a liquid state over a wide temperature range. The solvent should maintain in a liquid state over a broad temperature range, which means having as low a melting point as possible and as high boiling point as possible to accommodate the operation of batteries in a wide temperature range. Table 1 lists the commonly used linear and cyclic carbonates, ester and ether solvents, as well as their physical properties. In practice, it is challenging for a single solvent to meet requirements of low viscosity, high dielectric constant, low melting point, and high boiling point simultaneously. Taking carbonates as an example, cyclic carbonates have high polarity and a large relative dielectric constant. But due to the strong intermolecular forces, the viscosity of cyclic carbonates is also high, such as PC, EC. In contrast, linear carbonates can rotate freely, has low polarity and low viscosity, but their relative dielectric constant are also lower, such as DMC, EMC, etc. Therefore, in commercial electrolytes, a mixture of linear and cyclic carbonates is used to complement their strengths and weaknesses.